Hello and welcome. In this video, we're going to talk about absolute convergence versus conditional convergence and what exactly that means and how to show if something converges absolutely or if something only converges conditionally. So let's go ahead and jump in. So we have already shown in a previous video that the harmonic series diverges. But what do you think about the alternating harmonic series if every other term was positive, negative, positive, negative? I want you to hypothesize if you think that series would converge or diverge. So we're thinking about -1 plus 1/2 minus 1/3 plus 1/4, etc., etc. So hopefully you've had time to think about whether or not you think that's going to converge. And let's actually see if we can use the alternating series test to come to a conclusion here. So if we take the limit as n approaches infinity of the general rule without the alternating component, that's going to equal 0. So our first requirement is met. If we substitute in n plus 1 and compare that, the bigger the denominator, the smaller the fraction. So this is going to be less than or equal to that for n greater than or equal to 1. So both requirements are met. Therefore, the alternating harmonic series converges by the alternating series test. So that's kind of interesting that the harmonic series diverges if all the terms are positive, but the alternating harmonic series, if we're positive, negative, negative, positive, or vice versa, that series is actually going to converge by the alternating series test. In a way, that makes a little bit of sense. It seems like it's easier for a series to converge if half of the terms are positive and half of the terms are negative, because if I'm subtracting something and then I'm adding something, subtracting something and I'm adding something, going back and forth between those two things is helping our overall sum stay closer together and not have as dramatic of a change each time we're adding a term. So let's look at this in a little bit more depth. So as we just discussed, an alternating series or another series with negative terms in general has the potential to converge simply because the negative terms help the sum stay small. And if the sum is small, it's more likely to converge. There are many series, like we just talked about, where if we only look at the positive terms of the series, that series will diverge. But if we, in fact, get to look at an alternating version of that same series, then the series would converge. For example, we just talked about the harmonic series, right? The harmonic series diverges, but the alternating series converges. When that is the case, when we have a series that converges only when it's alternating, that's called a series that converges conditionally. The condition being it has to be alternating. So the condition is this series converges, but only when it's alternating. We call that conditional convergence. If a series converges regardless of whether it's half of the terms are positive and half of the terms are negative, then we would say that it is absolutely convergent. So let me give you a quick example here. We just said harmonic series converges conditionally only when it's alternating. When all the terms are positive, it does not converge. But if we looked at a series like the sum from n equals 1 to infinity of 1 over n to the third, whether or not this series is alternating, it's going to converge by the p-series test. If it converges when it's positive, right, we know this converges by the p-series test. We also could make it alternating. If it converges when all of the terms are positive, it's also going to converge when half of the terms are negative, likely using the alternating series test if it is alternating. So if a series converges when all of the terms are positive, we say that that series converges absolutely or is absolutely convergent. A couple things to note: a series that is not alternating and converges will automatically converge absolutely, like the one that we were just talking about. If this wasn't alternating, 1 over n to the third, that series converges absolutely because it converges when it's positive. What that means is if you can show that a series converges when all of the terms are positive, it also will converge when it's alternating, and you don't necessarily have to prove that. Any series that converges absolutely converges in its original state. So if you can prove that the absolute value of a series converges, or the absolute value of the rule, then you can conclude that the alternating series converges as well. If the original series, like the harmonic series, or even a series like 1 over the square root of n, if it diverges in its original state, then you need to see what happens if we look at the alternating series, likely again using the alternating series test. So let's look over some examples and decide if the series that we look at converge conditionally or converge absolutely or diverge, because it's possible that regardless of if it's alternating or not, it's still possible that it could diverge altogether. So we're going to determine if they converge conditionally or absolutely. If the directions didn't specifically say conditionally or absolutely, you would just do what we have been doing this whole chapter and perform a series test on the series that's given. But what I'm going to do is consider the series whose rule is the absolute value of the rule that's there. So I'm going to go ahead and write that out. So here's this exact same series, except we're just looking at the terms being positive. And we can use a comparison test to prove if this series converges or diverges. So go ahead and pause the video and determine if this new purple series converges or diverges using a comparison test. So the comparison series we would use here would be the sum from n equals 1 to infinity of 1 over the square root of n, which is going to diverge by the p-series test. So if we use, it looks like we're going to need to use the limit comparison test here. Nope, we could use direct comparison. So we can say that 1 over the square root of n and 1 over the square root of n plus 1, those are the two things that we're comparing. This purple series here is always going to be larger since this denominator is always going to be bigger. So since this larger series diverges, a smaller similar series will also diverge. So we can say, therefore, since the sum from n equals 1 to infinity of 1 over the square root of n diverges, so does the sum from n equals 0 to infinity of 1 over the square root of n plus 1 by the direct comparison test. Now, we just showed that this original series, when we only look at the positive terms, diverges. We haven't said what happens when it's alternating. So now we need to check the alternating series test to see if it does actually converge conditionally. If we could already say it converges when it's all positive, then we could say it converges absolutely. But right now, since this series diverges, our final conclusion is either going to be that our original series diverges or that it converges conditionally, meaning only when it's alternating. So I'm going to go ahead and look at the limit as n approaches infinity of 1 over the square root of n plus 1, which is going to be 0. That's the first condition for the alternating series test. Then I'm going to look at what happens if I compare the terms. This is going to have a larger denominator this way. This is going to be less than or equal to. Therefore, our original series from n equals 0 to infinity of negative 1 to the n over the square root of n plus 1 converges conditionally, only when it is alternating by the alternating series test. So again, my recommendation, first check to see if it converges when all of the terms are positive. Because if it converges when all of the terms are positive, it converges absolutely, and you don't have to check the alternating series. If it doesn't converge when all the terms are positive, just like we saw here, then you're going to have to go ahead and check the alternating series test to see if it converges conditionally. Let's go ahead and look at number 2. So the first thing I'm going to do is consider the series where all the terms are positive and find a comparison series to look at there. So I can just put absolute value around cosine of pi n to make sure the numerator is always positive. The denominator is going to be positive already. When I'm choosing a comparison series, cosine of pi times n means that numerator is either going to be 1 or negative 1. And I could probably rewrite this series so instead of having cosine, I either have 1 or -1, -1 to the power of n or n plus 1. I could rewrite it. However, I'm just going to leave it as is, and I'm going to compare this to the series of 1 over 2n. So the sum from n equals 1 to infinity of 1 over 2n. And I'm going to note that this diverges since it's the harmonic series, or it's 1/2 times the harmonic series, which means now I can use a comparison test to compare this purple series over here with my green one. So I'm going to go ahead and use the limit comparison test here. So I'm going to look at the limit as n approaches infinity of my purple series. So the absolute value of cosine of pi n over 2n plus 1 divided by my new series, or multiplied by the reciprocal of my new series. And this limit, since this is either going to be 1, actually since this is going to be 1 no matter what, this limit is going to be 1 over 2n plus 1 times 2n. That limit is going to be 1. 1 is greater than 0 and finite. Therefore, we can say our purple sum, the sum from n equals 0 to infinity of the absolute value of cosine times pi n over 2n plus 1 diverges by the limit comparison test. So now, again, like on number 1, my positive version of this series diverges. So now I need to check the alternating series to see if it converges while alternating. So go ahead and pause the video and look at the alternating series test on number 2. So using the alternating series test, the limit is 0. The terms are behaving in the way I need them to. Therefore, and I'm out of room, so I'm just going to squeeze it in the middle. Therefore, this series is going to converge conditionally by the alternating series test. Let's work through a couple more examples and then we'll wrap up this video. So when I look at number 3, my first thought is I can tell right away that this series is not going to converge when all the terms are positive, because the nth term test is going to give me that that limit is equal to 1, which actually means that even when it's alternating, it's not going to converge because, again, the limit is not going to be equal to 0 for the alternating series as well. So I'm actually just going to use the nth term test here and say that the limit as n approaches infinity, and I'm going to include the alternating part since I'm going to use the nth term test, n plus 3 over n plus 5. This limit is not equal to 0, therefore the sum from n equals 1 to infinity of -1 to the n times n plus 3 over n plus 5 diverges by the nth term test. I encourage you to pause the video and try and work through number 4 on your own and then unpause the video and see how you did. So first thing, I'm going to consider only the positive terms, and I'm going to compare that to the series 1 over 3 to the n, because if I'm looking at the absolute value of sine of n, that's going to be somewhere between 0 and 1 if I'm only looking at the positive terms, which means it's a good comparison series to compare it to 1 over 3 to the n. Because I can actually here say that 1 over 3 to the n will always be greater than or equal to the absolute value of sine of n over 3 to the n for n greater than or equal to 1. Therefore, we can say that our purple series converges, the series from n equals 1 to infinity of the absolute value of sine of n over 3 to the n converges since the sum from n equals 1 to infinity of 1 over 3 to the n converges by the direct comparison test. So what we just said is if we took this series that we started with and we made all the terms positive, if all the terms are positive, it converges. What that means is if some of the terms are negative, it's still going to converge. So we can say, therefore, the sum from n equals 1 to infinity of sine of n over 3 to the n converges absolutely. It converges absolutely because if it converged when all the terms were positive and then half of them are negative, it is still going to converge. So again, if you show that all the positive terms converge, you don't have to check the negative terms, or you don't have to check the alternating series. You can just simply look at the original one. Let's look at just one more example. And I'm going to encourage you, once I get this up on the screen, to try this one all on your own, start to finish. So here's the series. I want you to consider whether it converges conditionally, absolutely, or diverges. Go ahead and pause the video and work through it completely on your own. So we're going to consider the series whose terms are only positive, so the absolute value of cosine of n over n squared, and we're going to compare that to the series 1 over n squared, which we know converges by the p-series test, since p is 2 and 2 is greater than 1. Last time I checked, 2 is greater than 1. We can compare the rules or the terms for those series, and we can show that our comparison series, every term is larger. If every term is larger and this larger series converges, then so will the smaller version of it. Therefore, we can conclude that the series from 1 to infinity of the absolute value of cosine of n over n squared converges. What that means is we just showed this original series converges if all of the terms are positive. Therefore, the series from n equals 1 to infinity of cosine of n over n squared converges absolutely. So again, to recap, 7.7, absolute convergence means if all the terms of a series are positive and we can prove that it converges absolutely. As opposed to series like the harmonic series that only converge when the terms themselves are alternating. That would be called conditional convergence, meaning that it only converges when the terms are alternating. So a series can converge conditionally, can converge absolutely, or can diverge, meaning regardless of whether or not it's alternating, it's going to diverge. One important thing I want you to remember, you don't need to consider absolute versus conditional convergence unless a problem is specifically asking you about that. If you are just given a series and you're asked about the convergence of the series, you're not going to consider absolute conversion. You need to be specifically asked to consider absolute convergence to go down that path. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.